afternoon. Good afternoon, class. Our topic for today is about physical modeling, and we're going to concentrate on the examples of physical modeling as we go through this course. So we begin with the formula that we are going to use for the entire modeling process, and that is this. Configuration. No? So we are basically going to use the thermal resistance and the thermal capacitance. First, the thermal resistance. Now, how does resistance relate to the transfer of heat or the heat rate? So we have this formula. Let me put it here. No? So we have this Q. No? Q equals delta T over R, and R is the thermal resistance. So rearranging, we will have this this equation R is delta T over Q, wherein T1 is the higher or hotter temperature and T2 is the colder or the lesser hot temperature. Okay. Now, what is the unit for um, the thermal resistance? So the thermal resistance is the unit of centigrade per watts or Kelvin per watts. So so that equation come from this equation in the heat transfer catex thermal conductivity, then area, then times the delta occasion temperature over the thickness. No? So if we are going to uh, derive this, so if we are going to put these two, no, we divide both the numerator with the Ka, and here is Ka. So it's going to be delta T over X or L over Ka, right? So delta T over L over Ka. Okay? So the unit for this is temperature over watts, right? Temperature over watts, meaning degree centigrade, which is here, over watts. Okay? So the contraction of this will become watts only. How is that? So normally we have this Q over A. So if we put uh, the heat in terms of per square area, now, and what's gonna left is this. So temperature is this degree centigrade, and then the area um is under the heat. So what's gonna we have right now is this, yeah. So L over K, no? So meter over K, which is watts, no, per meter Kelvin, no? So watts per meter degree centigrade, no? If that is the case, degree centigrade. Okay. So if you rearrange this, now it's going to be uh, degree centigrade per watts because the meter and the meter will be cancelled, and what's gonna left is uh, watts, not degree centigrade per watts only. Now, the thermal capacitance. Before we go that, we have to consider this. Now, in terms of convection, the thermal resistance in terms of convection is this, right? You have to have this area, then H delta T, not T2 minus T1. And then if you are going to have this 1 over AH thing, now 1 over AH thing, that's going to be the so-called thermal resistance in terms of convection. And normally, if we put A here, no, so it's going to be 1 over H2. And if you are considering a pipe, if you are considering a pipe, there's a area here outside and there's an inside. So normally in the outside is HO, this is HI. So what's going to happen is that Q in terms of unit area, so it is the um, resistance now in terms of convection I plus 1 over HO. Okay, so let us have some example. So here, the number one problem is develop a model for the simple system of a thermometer temperature T being used to measure the temperature of a liquid when it suddenly changes to the higher temperature, meaning TL. No, so let me grab a pen. So there's a container. There's a container or a vessel, right? No. So this has a hot liquid. No. So that hot liquid or hot liquid is represented by the temperature TL, not T of the liquid. And then you put a certain device to read the measurement of the the temperature, which is called thermometer. So that is going to be T, right? Now, how do we model this? Now, so the model for this is Q equals delta T over R, which is Q delta T. The higher is temperature of the liquid minus the temperature at the thermometer over R, right? So that is the first model. And you're gonna equate this, no, this equation with the so-called thermal capacitance in that particular thermometer. So the thermal capacitance is C, no, which comes from MC, or small c, delta T. Now the contraction of this is just the thermal capacitance. So Q equals C, the derivative of the T, the temperature in that specific system, which is in the in the thermometer, right? So these two being equal, they are equal. No, we can equate them. No, so TL minus T over R is equal to C d over dt of T, right? So what we have to do is to cross multiply and rearrange. So TL minus T equals R C, the derivative of T. Now, so if we are going to model this, now d over dt. Now, so well, we can have the TL, the temperature of the liquid is the resistance times the capacitance, then the derivative of the temperature at the thermometer plus no, the temperature at the thermometer. So TL is this, no? RC d over dt of T plus T, right? RC d over dt of the temperature at the thermometer plus the rate of change of the temperature in the thermometer and the temperature of the thermometer equals the temperature of the liquid in that vessel. So that's going to be under the first order differential equation. Now, the next, we have here a room, no, which is presented by a cube, no, which is by volume, no. So there's a length, width, and height, and there's a heater. There's a coil here. There's a heater. So the heat coming from the heater is represented by Q1, no, and the one that is going outside is Q2, outside the room, at the rate of Q2, it's going outside. So the temperature here, outside is TO. Temperature inside is T1. So how do we model this? We can model this with this equation, no? So the capacity of this room is when you try to get the net quantity of heat, your Q1, which is higher, right? A higher flow, or I mean higher heat rate, minus Q2 is equal to the capacity of this volume. So this is the thermal capacitance over d over dt of T. right? Here, T. Okay. Now, but you can define Q2. Q2 is what? How do you how do you define Q2 in terms of this so that we can substitute here later? So Q2 is delta T over R, and the delta T should be coming from here, no? So Q2 before it goes up and it goes out, there is this not T1. Now T is that T1 or T or T only, right? So T, now there's a T here. Let me erase so that it will be clear now. So there's a T here, now T minus the temperature that goes out, which is smaller in quantity TO, and then the resistance, right? So there's a thermal resistance. So we're going to substitute this here, okay? So Q1 minus quantity T minus T outside over R is equal to C, the thermal capacitance, d over dt of T, right? So we're going to multiply the whole equation with the the R so that we can eliminate the R in the denominator. So we want to eliminate this. So R Q1 minus T plus TO, right? So minus T plus TO. Then we'll multiply this with R. Now C d over dt of T, right? So if we're going to get the RC now, RC d over dt of T equals what? This one equals RQ1. I just rearrange now. Uh, plus T outside minus T. Okay, so this is the equation, right? RC d over dt of plus T equals RQ1 plus T. Also, we can rearrange in that way. No, RC d over dt plus T. Now we can put it here. We can put it there. Then RQ1 plus TO. Okay, RQ1 plus T1. So this is the differential equation represented by the thermal capacitance and the resistance of that specific uh, room. No? So now we're going to model this. Now, for example, let's say example number 3. So we have a pipe. Oh, we have a furnace, right? So I'm gonna draw the furnace in a 3D model, right? So it has a thickness like that, no? And that thickness has a layer, 3 layers, one, two, three, no, 3 bricks, no? I'm gonna put a cutting plane here, no? And then get that section. So the section now is this, no? So there is this furnace na inside, and then there's a 3 layer, brick one, brick two, and brick three, right? So brick one, brick two, and brick three. Okay. So here, because the furnace, this the place where the flue gas, I mean the gas, no, the hot gas uh, goes through, and since it is a film or it is a gas, so it is by convection. So we can call it 1/H I, no, inside. So that's the thermal resistance in that convection mode. The, here is the outside. So this outside has air, no? So that's the temperature. I mean the temperature is ambient, no? So and the thermal resistance is HO, right? So by convection, the resistance by convection is what? 1/HO plus 1/HI. Then we're gonna get the so-called resistance for this, no? So in this L over K or X over K, so we can have this X1 over K1, and then X2 over K2, X3 over K3 of the brick, no? Because they have different thickness and thermal conductivity. So when you get the total resistance should be this, no? So delta T, I mean the resistance is this. So 1 over what? H I plus X 1 K1 plus X2 K2 plus Kx 3 K3 plus 1 plus H what is this plus HO. So 1 over H1, right? So when we do the so-called thermal resistance delta T over R total, it's going to be the temperature at the highest temperature there is, not temperature the of gas now inside the furnace minus the temperature ambient, and then the R total should be 1 over H, no? So it is 1 over H inside, no, plus x1 k1 plus x2 k2 plus x3 k3, and then plus 1 over the convective resistance 1 over HO. So this is right here, right? Delta T over RT, where in RT is this. Okay, that's the total resistance. Okay, RT is this. Delta T is temperature of the gas minus temperature at the air. No, so if you're going to equate that, no, so it's going to be Q, no, which is Q at the thermal resistance, and then here is the thermal capacitance. So here is delta T over R total, and then this is the Q here is MC, no? MC D over dt of the temperature, no? Temperature of the furnace, right? So we can have this like T of gas minus T of the ambient, then R total equals the mass, no? Total mass, then the total capacitance, then D over dt of the temperature at the of the gas at the inside of the furnace. Okay, so that's the model that we have. So the last one is this. We have here chamber. So how do we apply the thermal modeling in this chamber? So we have two chambers right now, and it's going to be the chamber one and chamber two. Then what we need to do is to model equation. No, so let me use I guess. So the thermal modeling, right? Thermal modeling for two chambers, right? Wherein the resistance is constant and the capacitance is constant also. Meaning the resistance is same, yeah. R equals R1 plus R2. And this one also, the capacitance at 1 is equal to the capacitance at 2. So let me draw the room, the, the two room. So here we have a room here, no? And there's a heater here. So this heater is designated by the variable Q, no? So this Q can transfer here. When it transfer here, it is Q, let us say Q2. Then when it goes outside, it is Q1, right? Then the Q2, the room 2, when the heat goes out, it is Q3. Then here the Q, at chamber 1, is represented by T. Is it T? Or let us say T1, right? Then the temperature at chamber 2 is T2. And all the temperature at the outside of this room is T3. No? So outside this room is T3. So how do we model? No? We can model the thermal resistance. How do we get that? Now the heat is Q, this one, right? Let me pull another color. So this thing here is Q minus, no? So it goes the out here and it transfer to the wall of the chamber 2. So Q1 minus Q minus Q1 minus Q2, no? So that is the net heat. And then this is the thermal resistance, right? The thermal resistance, in terms of thermal resistance, we can model that. And then it is also equal to the heat at the capacitance, which is, what is this? C, because C is M times C, right? D over dt of T. The D over dt of T. Now, what kind of T? T1 now, because you started here at the chamber 1 now. So we are referring to now. So this is at room or chamber number 1. So what do we do with this equation? Simply, we are going to use the general formula for the heat, no? Heat rate, no? Delta T over R, meaning delta T is higher, no? The higher minus the lower temperature. So in this case, Q, no, let me continue. So Q minus Q1. But Q1, no, Q1 is coming from what temperatures are involved, no? T1 is higher than the T3, no? T3 is outside, no? So T1 minus T3 over R, right? Because that's the definition of Q in terms of resistance. Then minus Q2, what is Q2? Here is Q2. It comes from the higher temperature T1 and then it goes to the T2. So T1 minus T2 over R. Then we just simply copy this d over dt of t1 because we are concerned about the chamber 1. So we evaluate this. No? So what's going to happen is that we are going to multiply r, right, to clear the denominator r, no, for the whole equation. So for the whole equation, we're going to multiply r, so it becomes r q. Then this will be eliminated. Then minus T1 plus T2. T3. And then this one, the R will be cancelled out. So we're going to continue minus T1, then distributive minus T2 plus it will become plus T2. Okay? Because it is preceded by negative sign. Then here, the R no, can be cross multiply with C d over dt of T1. So combining the similar terms, negative T1 is RQ negative T negative 2T1, right? Negative T1 and negative T1. Then plus T3 or plus T2 first, right? Plus T3 or plus T2. It's just the same. Then RC d over dt of T1. So if we're going to put it here, the resistance and the capacitance, you have to multiply, and then the answer should reflect that the change in the rate of temperature in the chamber 1, which is T1. Now, RC d over dt of T1, which is this, right here. And then here is what? Equals to R, then Q, right? Minus 2 T1, then plus T2, then plus T3. So this is our equation now, right? So let us see if that's correct. So RC, this is RC, d over dt of T1, right? RQ minus 2T1 plus T2 plus T3. So we are correct, right? RC d over dt of T1, then RQ minus 2T1 plus T2 plus T3. So let us go now to the second chamber. So the second chamber, so here's the second chamber. This one, right? So this one is the second chamber. The first question is, what are the concerned parameters here in terms of Q? So the concerned parameters here is Q2 and Q3. Let me pull out a blank now. So for chamber 2, so this is Q2, then this is goes out with the Q3, then this is T1, then this is T2, then this is T3 or T2, right? So since we are just concerned about the chamber 2, so the equation is this, no? Q2, right, minus, no, it goes out, we'll get the net effect. Q3 equals C d over dt of T2 because we are in chamber 2, no? So chamber 2 or room 2. So Q2 we already defined, no? So Q2 is what? Q2 is here, not T1 minus T2, because it just goes beyond this wall now. So, and the source temperature is T1, like before, T1 minus T2 over R. R is constant minus Q3. What is Q3 now? So Q3, before it goes there, the concerned temperature or higher temperature is T2 minus T3 over R, right? Equals C d over dt of T sub 2. So all we have to do is to clear the R. We're going to multiply the whole expression by R. So it will be clear out. So T1 minus T2. Then this one will be cancelled now. So minus distributive minus T2 then plus T3 minus T2 plus T3. So R will be removed, then this one we're gonna multiply this with the R expression. So R times C d over dt of T2 because we are in the chamber 2. So minus T2 and minus T2, they are just the same. So algebraically we can add them together. So T1 minus twice the T2, which is this, plus T3 is equal. So let me put here on the other side, which is basically the same. R times C d over dt of t. So that is our equation, no? RC d over dt T2, T1 minus twice the T2 plus T3. So let me see this. The answer, if that is correct. So RC d over dt of T2 then equals T1 minus 2T2 plus T3. Minus 2T2 plus T3. So let us go check RC d over dt of T2, chamber 2, T1 minus twice the T2 plus T3. So that is our modal equation when we consider the two chambers in thermal modeling, wherein resistance is the same for uh, two chambers, and the capacitance also is the same because they have the wall thickness the same and the length with height is the same. So thermal capacitance is constant for the whole system, and this is the answer or the model equation, differential equation. Okay, so I hope you learned something. Thank you very much and have a good day. Thank you.